Welcome to Ask and Learn.
Okay, well, in problem 17, we have to repeat problem 16 with constant specific heat at room temperature. And as we know, in problem 16, we have air standard process cycle, with four processes. So let's put here the diagram. So we have to repeat the problem, which means we have to describe the PV and TS diagram from problem 16. So let's see. This is the PV. We know that the first process is a process with constant volume, which means that we have a vertical line in PV diagram. The second process is a process with constant pressure. Therefore, we have a horizontal line in PV diagram, constant pressure. The third process is a process with is an isentropic process. An isentropic process is represented as this hyperbolic curve in here. And the final one, again, is a constant pressure process. So let's do it here. This is not good. Okay, now it's better. So let's put the points in here. This is 1, 2, 3, and 4. Isentropic process means that we do not have exchange of heat with the surroundings. Okay, and the heat in this process enters in 1, 2, enters in 2, 3, and leaves in 4, 1. Now let's do it the TS diagram. So the TS diagram is going to be a little more complicated. It's not so intuitive. Well, in a TS diagram, first of all, the isentropic process is described by a vertical line. So this is the 3, sorry, this is the 3, 4 process. And the other process is going to be this one. So we have here this, we have here this, and we have here this one. So this is 1, this is 1, this is 2. Again, the heat enters, enters, and leaves. And this is a TS diagram. Okay, so that's the first item. The second item of this problem, we have to find what is the heat input. And as we know, the heat input in this problem, as we can see, is the heat from 1, 2 plus the heat from 2, 3. Okay? The only way the heat enters the system. Okay, we know that 1, 2 is 300. Therefore, we just need to find what is 2, 3. And to find the heat 2, 3, let's put in here. We know that this is just the change in the internal energy. Therefore, CV T2 minus T1. And we also know, sorry, that is not correct. I do it wrong. The numbers here. So this is going to be 1, 2. The transition 1, 2 is the change in the internal energy. The process 2, 3 is the change in the enthalpy. So this is the change CP T3 minus T2. And as we can see, the only problem to calculate the heat to 3 is to find what is the temperature 2. So let's take the temperature 2 from here. Therefore, Q1 is just 300. So this is 300 times 0.171 specific heat to constant volume. T2 minus T1, which is 540 R. Calculating this, we find that the temperature 2 is precisely 2294. Okay? Well, with this temperature, we can come in here and calculate what is the input heat in process 2-3. So this is just 0.24, the CP, that multiplies 3200 minus 2294. Therefore, Q23 is just, let me see, 217.4. Now that we have the input heat, we can calculate the entire answer, and this is going to be precisely 517.4 BTU LBM. Okay, the last thing is to find what is the efficiency. So the efficiency of this cycle is just 1 minus Q out divided by Q in. Well, who is Q out? Q out is going to be the change in the enthalpy. So it's just Cp T4 minus T1. And how do we find T4? Because we have a problem here. Who is T4? Well, let's do it here. We know that the transitions between 3 to 4 is an isentropic. Therefore, an isentropic transformation is described by T3, P4, P3 to the power of k minus 1 divided by k. This is going to be equal 3200R, 14.7 divided by 62.46 to the power of 0.4 divided by 1.4, which gives us a temperature 4 of 2117 R. Therefore, if the temperature 4 is this one, we can find from here that Q41 is going to be 0.24 2117 minus 540, which gives us 378.5. Okay. Okay, so since we have the output heat, we can finally calculate this as 1 minus 378.5 divided by 517.4, which gives us an efficiency of 26.8%. And that's the final answer to this problem. Thanks for watching.